Alright, so in this video I'm gonna be explaining this important paper with the title Motif-Driven Subgraph Structure Learning for Graph Classification. This paper in 2024. Motif is a kind of structure. Also, if you are working on interpretable graph neural networks, that is very essential. You can capture it with kernels, with many different ideas like anonymous random walk, to have a better interpretable graph classification. But this paper is just talking about motif-driven subgraph structure learning for graph classification. To mitigate the suboptimal nature of graph structure learning has emerged as a promising approach to improve graph structure and boost performance in downstream tasks. Despite the proposal of numerous GSL methods, the progresses in this field mostly concentrated on node-level tasks, while graph-level tasks such as graph classification remain largely unexplored. Notably, applying node-level GSL to graph classification is non-trivial due to the lack of fine-grained guidance for intricate structure learning. Inspired by the vital role of subgraph in graph classification, in this paper we explored the potential of subgraph structure learning for graph classification by tackling the challenges of key subgraph selection and structure optimization. We propose a novel motif-driven subgraph structure learning. Specifically, it incorporates a subgraph structure learning module which can adaptively select important subgraphs. A motif-driven structure guidance module is further introduced to capture key subgraph level structural patterns. We call them motifs, and facilitate personalized structural learning. In biology we call them motifs, but they are wider than this. Extensive experiments demonstrate a significant and consistent improvement over baselines. So you see the problem of the coarse-grained supervision in graph classification. So each graph, we have two challenges. Each graph may comprise a large number of subgraphs, yet only a finite subset is valuable for the final graph level prediction. How to accurately select key subgraphs from a vast pool while optimizing their structures to aid in the graph level test. The second challenge is subgraphs from graphs of the same category often exhibit discriminative structural patterns, which is valuable for graph level tasks. How to effectively capture representative motifs of each graph category and guide the structural learning of subgraphs. So the methodology is this. We have conventional graph structure learning paradigm that says numerous graph structure learning methods have been proposed for node-level tasks. Despite their diverse designs and implementations, recent works have found that most of them can be reformulated into a unified paradigm, which includes a graph learner and a processor. So the graph learner is used to compute pairwise edge scores, producing a similarity matrix. Subsequently, the learned adjacent matrix is further refined by the processor. Commonly used techniques include k-nearest neighbors, epsilon nearest neighbors, concrete relaxation, symmetrization. Finally, the learned structure is fed into the backbone GNN to learn representations for downstream tasks, such as graph-level tasks. So this is a framework of proposed method, including the subgraph structure learning module and a motif-driven structure guidance module. We conduct structure learning on subgraphs separately and use a gauge mechanism to adaptively combine the learned substructures. Important subgraphs are then filtered as candidate subgraphs, based on which motif alignment and motif extraction are iteratively conducted. So we have this part subgraph structure learning. Then we give it to refine subgraph. We find the good subgraphs. Then we give it to candidate subgraphs. So from this candidate pool, we do clustering and extract pattern from candidate subgraphs. Then we give it to subgraph motif alignment. So this is an extension of the conventional graph structure learning. We first partition the graph into several subgraphs and estimate their importance. Afterwards, we conduct structure learning on these subgraphs respectively, and the learned substructures are adaptively integrated according to their importance. Various techniques can be employed to partition a graph into case subgraphs. So, for the simple breadth-first search algorithm, this reference has done. And for a given graph, we first sort the nodes based on their degrees and designate the top k nodes as the central nodes for the subgraph. We then utilize breadth-first search to extract a subgraph for each central node, with maximum number of nodes in each subgraph limited to m. The specific values of k and m are determined based on the scale of the datasets to ensure appropriate coverage on the original graph. We need to estimate their respective importance score. Here, we use a GNN-based encoder to obtain representations for each subgraph. The importance score for each subgraph is calculated using this equation. Now, P here is just a learnable vector. So we perform structure learning on these subgraphs to obtain refined graph structure. So we treat each subgraph as an individual entity and focus only on the local characteristics of subgraphs during structure learning for each subgraph, so thus avoiding interference from other irrelevant parts. Then with the learned substructures, we adopt a gauge mechanism and adaptively combine them to obtain the final optimal graph structure. So gamma here controls the proportion of integration with the original graph structure. Unlike conventional GSL method that treat the entire graph uniformly, as GSL divides the graph into several subgraphs, learns structures for subgraphs independently, and utilizes importance scores as weights when fusing substructures. By introducing such a gate mechanism for subgraphs, SGSL has the ability to perceive the importance of subgraphs during structural learning, it mitigates the influence of irrelevant subgraphs, leading to more stable optimization under coarse-grained signals. Besides, the partitioning approach we previously used allows edges to be shared by multiple subgraphs. So with the refined subgraphs G sub I and estimated importance scores, we select subgraphs with a high importance score to obtain candidate subgraphs. Okay, so we have now introduced SGSL module, which conducts structural learning at the subgraph level and adaptively selects key subgraphs. Intuitively, subgraphs from graphs of different classes exhibit distinct structural patterns, which can be viewed as a target for structural learning in the subgraphs. So we iteratively perform subgraph motif alignment and motif extraction. For each mini batch, these candidate subgraphs will be mapped to motifs belonging to the corresponding class, evolving into subgraph motif alignment loss. So the candidate subgraphs are collected across multiple mini batches in an epoch and are clustered to update motifs in a class-wise manner. So this is a subgraph motif alignment phase that we have obtained. Assume we have obtained a series of motifs capturing essential structural patterns for subgraphs across different classes, indicating the class to which each motif belongs. The challenge lies in mapping the learned substructures with the corresponding motifs. Since the graph matching problem is computationally intractable, we opt for modeling motifs from a representational perspective. Namely, we represent motif as M. Therefore, computing a match ratio between the learned substructures and motifs becomes straightforward. So this is an encoder, it's a GNN-based encoder. Phi is just a function that calculates similarity between two representations. So remember here, MI is just a motif. So the similarity between your encoder and the motif, phi combines this phi is the similarity, then you get this S. So you get this similarity. So treating motifs of the corresponding class as positive samples and motif of other classes as negative samples, we develop a contrastive loss that enforces the learned substructures to align with the specific motifs. So motif alignment loss provides diverse learning targets not only for subgraphs from different categories via label-aware motif matching, but also for subgraph within the same graph via the use of mean instead of sum in the numerator. The remaining problem is how to effectively extract key patterns as motifs. So we decide to cluster candidate subgraph in a class-wise style and use the centroids to update representations of motifs belonging to the corresponding class. We update motif representations using k-means algorithm for simplicity. So within each class, we employ the original motifs as initial centroids and consolidate the representations of the corresponding subgraphs via k-means. So candidate subgraphs from graphs of a specific class are used as a source for extracting corresponding motifs. So in summary, it conducts structural learning at the subgraph level, identify important subgraphs via SGSL module, and motif extraction and subgraph motif alignment work in an iterative manner, in that in each epoch the model is trained in an end-to-end manner by optimizing the subgraph motif alignment loss. Then every eta epoch we update the motif using collected candidate subgraphs. So they did it for IMDb binary. This is for movies. If it's actor, and enzyme protein, we use this for all of them are for graph classification, and we can compare the accuracy of graph convolution with this approach.